we are still balanced. Is the coefficient stand for balancing equation? That's why. Okay.
Okay.
All right. So that's the balanced equation. From a balanced chemical equation, we know how many molecules. This is this. So balancing will tell you that. We'll give it a number of molecules, number of moles, number of liters, and so on from the balanced equation. React with how many moles of product are produced. That was your question. I'm glad you asked that question because they give you an answer now. If there are gases, we know how many liters of gas react or are produced. Particularly table 9.1, interpretation. This is what we're doing this morning. This chapter is about interpreting things that we learned before. All right, plus additional things. Interpretation of chemical equation coefficients. For the general equation, here's a general one. General thing, 2a plus 3b give you c plus 2d. That's general situation. So the ratio of molecules will be what? 2 to 3 to 1 to 2. So the molecules are based on balanced equation. The ratio of moles will be 2 to 3 to 1 to 2. The ratio of volumes will be 2 to 3 to 1 to 2. Everybody see that? It's based on the balanced equation. All right. All you need to do is interpret it the way you want to interpret it. All right. The law of conservation of mass. Mass is conserved. We're talking about matter now. Enter the occupied space. Don't forget, all this stuff is all about matter. Chemistry has concern for matter, so we study matter. The law of conservation of mass. What does it say? That mass is neither created, which we heard that before, nor destroyed during a chemical reaction. That's one of the reasons why everything on the left-hand side is the same stuff on the right-hand side, because of conservation. You see, the UV there, UV light is a catalyst. So again, it's the same reaction. So now, more interpretation. So we see NO, how many grams is all that? So that's the nitrogen plus the oxygen, all right? Times that by 2, that's interpretation for gram. And the oxygen is a molecule, each one is 16. So therefore, 1 times 32.00. And all that stuff there, if you add them up and find the molar mass for NO2 gas, which is 46.01 for each one, times 2, you see 92.02 will give you 92.02 mass is conserved. Mass is conserved. That's what we're talking about here. Mass of the reactants is equal to the mass of the product. Mass is conserved. Mass is conserved. Conservation of mass. Nothing is destroyed. It said that mass is neither created nor destroyed during a chemical reaction. They bump into each other and they form something new, but when you go and check what's on the left-hand side, once you go to what's on the right-hand side, mass is conserved. All right, so we moving right on, we said we can use a balanced chemical equation to write mole ratio, which can be used as unit factors. The mole ratio can turn into unit factors. The unit factors are fraction, okay? Numerator over denominator. Unit factor, remember when we're solving the problem? The 3-step problem, step number 3 is the unit factor. So therefore, here we go. Since 1 mole of N2 reacts with 1 mole of O2 to produce 2 mole of NO, we can write the following mole relationship. 1 mole of N2 over 1 mole of O2, 1 mole of N2 over 2 moles of NO, 1 mole, these are the factors you set up These factors are designed for calculation.
Eva,
Yeah.
tomorrow,
28.
the brother.
Mhm.
Oh, that's one of yours. Can you?
Whoever is talking, I'm waiting for you. You have a question? All right. So how many moles of oxygen react with 2.25 mole of nitrogen? Back to mole. Mole is like dozen, 12 things equal to something, anything. All right. So that mole is 6.02 times 10 to the 23rd. It could be particles, it could be ions, it could be molecules, and atoms and so on that we counted. So here's another homogeneous reaction. We want more. So here we go. We want more of O2. Same concept. So all your homework problem must be set up this way. All right. I will not even look at them if you don't have these steps in your homework. I will not even look at your homework. So in all the problem solving, those 3 steps I want to see for every problem, those 3 steps. Step number 1, step number 2, step number 3. Very important. Otherwise, I will not grade your homework if it doesn't have those steps. So make sure you do that. Don't say I didn't warn you. All right. So we have the 2.25 mole of N2. So now we select the factor appropriate for this calculation. So because we want to get rid of mole N2, so the mole N2, whatever you're trying to get rid of should be in the denominator. So it's gone. We got mole O2. That's our concern. So now we got 2.25 mole O2. This is the way the problem should be set up. All the problems that you have must be set up this way. The 3-step first, then followed by the problem itself. And the significant digits must be significant. All right. So critical thinking, let's think critically. What is the difference between iron and steel? Iron and steel. Start thinking. What is the difference? Iron is a pure element. Fe, pure. Steel, we got to put some stuff in there, make it alloy. Alloy is a mixture of metal to make the iron look great. So it can't rust. So when you go to the restaurant, you don't see iron. They got steel everywhere because they do not attract oxygen in terms of reacting with oxygen. There's stuff we put in the iron that will not allow the reaction of oxygen. So we'll call that steel. So to make it look great. So steel is an alloy. Alloy is a mixture of metal. So steel is an alloy of iron with other elements, just so it will not attract oxygen. No rust. You see, steel is very expensive. And that's one of the reasons why we don't make steel out of everything, because it's very, very expensive. All right. Certain things, like kitchen utensils, you need to have steel equipments. There are certain things you need steel for, not everything.
So is steel stronger than iron?
Oh, yeah. Mm-hmm.
Okay.
Other elements are included in steel to impart special properties, such as its increased strength. Did you answer your own question?
Oh, yeah.
Increases strength. They're resistant to corrosion. Corrosion is a big problem in the United States. Okay? And so those industrial countries are fighting very hard. But if you're in a little country that they can, hardly make it there, they're not going to worry about steel because, that's less of the problem. They want something to eat. They're not even worry about, but here we face so many problems. Corrosion is a big problem here in the industrial nation. So steel, you can see how steel is made. You can see that set up there for steel. Common additive elements in steel include carbon, manganese, chromium, and there's also we use molybdenum. And it's not listed here. All right. So you got to put that in there in the iron. For copper there, for manganese, we got cast iron, and we have, steel and chromium. So those are all expensive stuff, and these are transition metal are very expensive. Transition metal are very expensive. All right. Chemists and chemical engineers, I'm both of those. I'm a chemist first before I became a chemical engineer. All right. So I'm both. Chemists and chemical engineers must perform calculation based on balanced chemical reactions to predict the cost of processes. The chemical engineer, dollar sign is the thing. We go after the dollar. Dollar is number one, making money. In chemical engineering, it's all about making money, dollar sign. We amplify, we make things bigger, and we make, we build factories and manufacture things to make money. These calculations are used to avoid using large excess amounts of costly chemicals. So before we make anything, we do all the calculation, making sure we don't waste anything. Making sure. So all the calculation. So when you do this, when you do the calculation, everything just fit in place. But the people who don't know how to think about doing calculation, but they waste a lot. They waste so much. Now people, if you're in the kitchen cooking before you cook that meal, make sure you calculate everything that you're gonna be before you waste stuff, put stuff in the trash can. When you leave there today, make sure that you're gonna measure everything that you're gonna use in that kitchen when you're making a nice meal. Measure everything. You'll not be wasteful. You save yourself a lot of money. Calculation. Okay. These scientists use are called stoichiometry calculations. Stoichiometry calculations are very powerful. You have chemists do that stoichiometry, and chemical engineering do that. They're big on that. That this is where you save a lot of money now, wasting a lot of material. Stoic. All right, types of stoichiometry. There are three basic types of stoichiometry problems. We introduce in this chapter, and pay attention, three of them. You give it a mass and you go into a mass. You give it a mass and you go into volume. You give it a volume, you go into volume. Three major stoichiometry problems. Now we're gonna go through them this morning. So take a deep breath, tighten your belt, drink some water, and be ready. Give it a mass, go to mass. Give it a mass, we need volume. Give it a volume, we need volume. These are the three major things that are done by the chemists, by the chemical engineers. All right. So let's do the first one. In mass stoichiometry problem. How do we do that? We will convert a given mass of a reactant. So we build reactors for chemical engineer because they do things on a large scale. So they design reactors where is all the stuff to measure, they put them in our reactor for the reactor to take place. Now, right now, I'm making mouthwash. I have my little reactor here. I get my cinema. I go downtown, buy cinema sticks, and I extract from the cinema sticks and make my mouthwash. So I don't know when I will catch up with you one of these days, but I'd like to give you a sample. All right. And a product to an unknown mass of reactant, a product. There are three steps. Let's take a look at the three steps. Slowly. Convert a given mass of substance to mole. So I told you that the mole is a trampoline. Everything you do, you got to go to the mole. You go to the mole. All right. So you take that given mass, we're going to convert to mole, using the molar mass of a substance as a unit factor. So the molar mass becomes a unit factor, which is gram per mole. Gram per mole or mole per gram, we can you know convert that. If you're looking for gram stays on top. If you're looking for mole stays on top. All right. So in top we can interpolate that, and so therefore we say number two, convert the moles of a given to a mole. So if you're given something in mole, you can take it a mole. This is the easier step. Number two is easier compared to number one, because number one, you got mass. You gotta go to, if you go from mass to mass, so you gotta come from mass, you go to mole, then from mole, you go to mass. Step one takes a lot of work. So usually when I give an exam like that, I stick with step number one. I give the student number one because I want the student to do some work. Make you work. So therefore, I don't normally give them more to more. No. That's cheap work. That one is cheap. All right. So converting moles of an unknown to grams using the molar mass of a substance as a unit factor. So these three steps are very important. All right. So this is mass of mass stoichiometry problem. All right. So here's a problem right here. Now let's watch this problem. I'm going to be asking some questions here. This reaction here, what kind of reaction is this? Somebody tell me.
Is it decomposition?
Very good. Let's celebrate that. Who said that?
Anakin.
Anakin, you want to borrow this money.
Thank you.
All right. So we're going to break this down to smaller pieces. The question says, what is the mass of mercury produced from the decomposition of 1.25 gram of orange mercury 2, that 2 there, meaning is a what? Stock system, okay? Transition metal, oxide. So the first thing that comes to our mind, what is the molar mass of mercury oxide? We're going to find the molar mass. We got a molar mass, it's going to be used as a conversion factor in step three of your problem. All right. So the first thing we want to do is we have a nice balanced equation. The equation must be balanced. Because the equation is not balanced, whatever you do, it will be wrong. Make sure you have a clean, balanced equation. All right, so convert grams of mercury to mole of mercury using the molar mass of mercury, which is what's given to you. The molar mass of that is gram two. If you look at a periodic table, you add up the mercury plus the oxygen, right? That's a molar mass. Add together. Convert the mole of mercury to mole of mercury oxide using the balance equation. Convert the mole of HGO to grams of HGO using the molar mass. Do you see those steps right there? Because the question, what does the question say? Pay attention to the question. What is asked? What is the mass of mercury produced? So what I allow students to do, you put this thing in boxes, okay? Put a given in box and put whatever is given to you over that box. Then what they're asking for, you put that in box too, and put an X, whatever is X mole, X volume, X gram, you put that there. So now you know what you're dealing with. Easier way to deal with that. All right. You put boxes on the things that they are specifying in the problem. All right. So here we go. So the equation is balanced nicely. So we start with our given. We're given 1.25 gram of mercury oxide. Don't use the coefficient in this system here. Just what you are given. The coefficient is there for some other reason. Okay. Now, you see the coefficient will be used as a unit factor, ratio-wise. So 1.25 gram of HGO. So the first factor is the molar mass factor, which is mole per gram. 1 mole of HGO weigh how much? 216.59 grams per HGO. That factor is very appropriate, all right? So that we'll get rid of the gram HGO. So the gram HGO is gone. We are now in mole HGO. Now, look at the next factor. That factor comes from the balance equation. The reason why you must have a right balance equation, there's right there, the second factor. The 2 moles, they're asking for, the problem is asking for gram of Hg. So the ratio must be between what's given to you and what they're asking for. Do you see that factor there? 2 moles of Hg. You don't see oxygen there. They're not asking for oxygen. Oxygen is part of the equation, but the problem is not asking for oxygen, asking for mercury. So we're going to go, what is the ratio between the mercury and the mercury oxide? That's very, very important. The reason why the equation must be balanced properly. So therefore, that ratio is 2 moles of mercury to 2 moles of mercury oxide. Must be there. Now, so therefore, the mole of Hg, you see, as we go from left to right, the thing we start with must disappear. And what we're looking for must remain. So now, how do you get rid of 1 mole of HgO based from the balance equation? All right, the factor from the balance equation. So more Hg cancel more Hg. Now we're getting closer. More Hg. We got more Hg. We got more Hg, but the question says, how many grams of Hg? So we're coming from mole and we're going to gram. So you see the problem there? Mass to mole to mole to gram. You see why I like this one? Given the mass, because there's a lot of work you must do. And I love to see students do a lot of work. That's how they learn. All right. If you email class, you never get a rest. You never get a rest until that day of the final. You'll be working, make you work every single day. There is no break. I guess you know that by now. All right. So by now we have, but don't go tell your friends out there, say I'm not taking his class. So therefore, so the more Hg cancel more Hg. What's left? We got gram Hg. That's what we need. So then we do the math. Take your calculator. Do the math now. Now let's take a look at the numbers. You know, significant digits is following you in this course. So the first one has 3 significant digits. The second factor got 5. And then the last one got what, 5? So therefore, according to the rule of multiplication and division, you take the one that is smaller. So because 1.25, that's 3 significant digits. So the result in the answer should be 3 significant digits. All right. Those things I want to see in your homework. When you do any homework problem that had something to do with math, it must be set up correctly like this. If it's not set up like this, I will not even look at it. All right. Now, so we've done mass, stoichiometry. Now we're going to go to mass volume. You give it a mass, oh, this is it. But students see, say, how can you come from mass and go to volume? Student asks that question. How do you do that? Oh, we're going to find out now. In a mass volume stoichiometry problem, we will convert a given mass of a reactant or product to an unknown volume of a reactant or product. Pay attention to that. In the mass volume stoichiometry problem, we will convert a given mass of a reactant or a product to an unknown volume of a reactant or product. Let's see how that happens. 3 steps. There are 3 steps as well. Convert a given mass of a substance to mole. That mole is, I told you, it was a trampoline. You cannot go by. You know that mole, you can't go anywhere without coming to mole. You gotta stop at Mo is there. He is so generous. He is ready to entertain you. He says, stop by my house. You know, what do you need? Coffee, cream, whatever you need. Come to me. The coefficient in a balance equation. Balance equation. You hear that balance equation? Coefficient in a balance equation. The equation must be balanced. If it's not balanced, you're wasting your time. You're not going to get anywhere. Number 3, convert the moles of the unknown to liters using the what? The molar volume of a gas. That's why I say, remember that? The molar volume of a gas, which is what? 22.4 liters per mole. That number you should have in the palm of your hand. 22.4 liters per mole. So when you hear mass volume, so it can be a problem. The guy that gets you out of there is that molar volume of a gas. All right. So therefore, here's the problem here. You read the problem, it says how many liters of hydrogen are produced. I mean, it got to be on the product side. Are produced. You hear that? When a reaction of 0.165 gram of aluminum metal with dilute hydrochloric acid. So we take this metal here, drop in acid, reaction begins. Now, can somebody tell me what kind of reaction is this? What reaction is this? Who's there? Anybody?
Is it a single replacement?
Single replacement. You again. Very good. Single replacement. So now, to do single replacement, what must we consider? What do we talk about? Anybody remember what we talk about in doing a single replacement?
A more active metal displaces a less active metal.
And what is that called? What's that? But how do we call it? Nobody remember?
Is it the activity series?
The activity series. Very good. Oh, this guy is scoring some points this morning. I'm marking it down. Let me mark it down. All right. Activity series. So you go in activity series, okay, is alumina above hydrogen or below hydrogen? That is a $1 million question for the day. So you look at your series, yeah, this guy way above hydrogen. So therefore, he can knock out hydrogen from there. So he takes out, so the collision will take place. The alumina will collide with HCl. So when they collide, alumina takes the place of hydrogen, and then we release the hydrogen. Hydrogen is by itself now. Hydrogen gas as a gas. Diatomic, can stand by itself, so therefore it's a diatomic. What kind of reaction is this? Is it heterogeneous or homogeneous?
Hetero.
Heterogeneous, very good. Who said that? Christine, very good. All right. Now it's time to balance this equation. What did we say? We look at a species that is what? More complicated. More complicated. Look at a species that is more complicated. All right, we identify that species, then we balance the equation. Now, is the equation balanced? Anybody?
No.
It's not? It's not balanced?
Oh,
It is.
Yeah, it is.
It is balanced. Okay, very good. So convert grams. So now we are giving 0.165 gram of aluminum metal. That's giving. So we put a box right over the aluminum. Inside our box, we put in 0.165 gram. And they're asking for, they said, how many liters of hydrogen will be produced? So we put a box over hydrogen and pour X liter. So now you know you have isolated aluminum and hydrogen. Those are the two that you're working with in this equation. And make it easier that way. I advise you to do that. Put a box over what is given, put a box over what they are asking you to find. That way you know what I'm dealing with, what the ratio will be, the ratio of giving to what they're asking for. All those things you start playing. Convert grams of Al to moles. So we'll go to mole. Start by moles house. Using the molar mass of aluminum. Go on the periodic table. The molar mass becomes a what? Unit factor. It's a very good unit factor. Look at periodic table, we see aluminum at 26.98 grams per mole. All right. Convert moles of aluminum to moles of hydrogen. So we take that moles we got from aluminum, we're going to change that mole to mole hydrogen. As you go from left to right, things are dropping off, and the solid material will be gone. But then you get to the end of the right. So therefore, using the balance equation. Now, convert moles H2 to liters using the STP. What is the STP volume? The molar volume, STP. STP, what do we know? The temperature is 0 degrees Celsius, and the atmosphere is 1 atmosphere. And the volume is 22.4 liters per mole. So then you see STP. There should be a flashback. STP. All right, that should be a flashback right away. All right, so now, here's the setup. Here's the equations balanced nicely. So here's the setup now. We're going to change the 0.165 gram, which is 3 significant digits. The first factor that follows that is the molar mass factor. 1 mole of aluminum weighs 26.98 grams of aluminum. So gram of aluminum cancel gram of aluminum. So now we need more aluminum. Our destination is volume, is liter. So now we need this factor right here, the ratio. What is the ratio of aluminum to hydrogen? So the thing that you're looking for should be on top in terms of the ratio. So we look at the hydrogen, we see 3 moles of hydrogen gas. Aluminum, 2 moles of aluminum. That factor is very appropriate. So aluminum is gone for good now. It disappears as we go closer to the right. So more aluminum is gone. We are now in more of hydrogen gas. But we're looking for volume. So now, we know our STP, the volume is 22.4 liters of any gas. Any gas can occupy this volume. No matter what size it is, 22.4 liters of H2 over 1 mole of H2. So the more H2 gone, so the problem is in volume. That's what the question was asking for. So when you do the stoichiometry problem from mass to volume, remember your molar volume. So therefore now, the result is 3 significant digits as well. All right, any questions so far? All right, so that is the mass volume problem. We did a mass volume. So if I were giving you a test, in a regular setting or even on this one, I will give you number 1 and give you the mass volume problem. You gotta know, you start thinking about How do I get from mass to volume? Students ask that question. How do I do that? Do I need an airplane to go? Do I need that? Do I need a boat? Do I need what do I take to go there, to get there? All right. So here we go. We count the volume. How many grams of sodium chlorate are needed to produce 9.21 liters? They're telling you, what do I start with? I want to make 9.21 liters. My goal is to make that. Well, how much material do I need to give me this volume? The previous problem, you are given the material and you define the volume. Now they're telling you, this is the volume you should make. So let's say you got a job and working for some company, and your manager comes to you and say, look, I want you to make 9.21 liter of oxygen gas. All right? Then you stand right there, scratching your head, and you say, let me go get my aspirin. I need some aspirin for this. All right. So therefore, he says he wants 9.21 liters of oxygen gas. So you go on your shelf, you got to do some kind of reaction. So this is sodium. He said, he's nice to you. He said, use sodium chlorate. Use sodium chlorate. So now, what kind of reaction is this?
Decomposition.
Decomposition. Who said that?
Chanel.
Chanel. All right. Mark you down, Chanel.
Okay.
All right. Decomposition. So convert liters of O2. So the equation must be balanced. First thing, have a clean, balanced equation. Convert liters of O2 to moles of O2. So therefore, you start with a given. And then 9.21 is on the product side. It's on the product side. That's what you're making. But what material do you start with to make that? So you start with that. Start what's given to you. So we see now, so the ratio is going to be, so you put a box over sodium chlorate, put a box there, the question says how many grams do you put X gram in that box? You go to the oxygen, you put 9.21 liter in that box over the oxygen. So now your ratio will be between sodium chlorate and the oxygen, not the sodium chloride. So sodium chloride is there, but the problem is not calling for that. So now, we need a molar-mass for sodium chlorate. We need a molar-mass for that. All right? So how do you get a molar-mass? You go on there. What I want everybody to do, take your pencil and paper and justify 106.44 right now. Look at the periodic table, see how they got that. Let me give you some time to find out how they got 106.44.
Is it the molecular weight?
Have you done it?
Huh? Well,
That's the molar mass we talk about over and over.
okay.
I want you to do it and tell me what you did.
You add the mass of each NaCl and 3 times the oxygen. So
Yeah.
22.99 plus 35.49 times plus 16 times 3, and you get 106.44.
Very, very good. All right. So that's what we call molar. All right. So now we start with a given 9.21 liters of oxygen. So this factor here, that's the STP factor. STP factor, the second factor, the first factor is STP factor. That get us out of liters. One more O2, about 22.4 liter O2. Now we are in mole ratio. So we get, so from the balance equation, 2 moles of sodium chlorate over 3 moles of oxygen. So the more oxygen is gone. We're in more sodium chlorate. So now the next factor is the molar mass. The molar mass factor. 106.44 gram of that over 1 mole of that. And so the result is what? For the 9.2 grams of that, if it's done correctly. So that is what we're talking about. If I give you anything, I'll give you volume, mass to volume, mass to volume. That's what I would do. I'll give you the mass to mass and mass to volume. Most of the time, I will not give you that volume to volume. All right. All right. So anyway, Gay-Lussac, we'll be talking about gases. Gases. We'll be dealing with that tomorrow. That's chapter 10. And we'll talk about it. Gay-Lussac will show up again. All right.
Are we dealing with chapter 10 tomorrow or on Tuesday? Or
tomorrow is Tuesday.
Oh, okay.
All right. But tomorrow is Tuesday. So Gay-Lussac discovered that volumes of gases undergo similar conditions combine in small whole number ratios. Whole number. Again, whole number start from 0 on the real number table. This is a lot of combining volumes. Lot of combining volume. All right, what reaction is this one here?
Combination.
Combination, very good. Is it homogeneous or heterogeneous?
Homogeneous.
Homogeneous, very good. All right. So here we need a balance equation. In every case, balance equation. 10 ml of H2 reacts with 10 ml of Cl2 to produce 20 ml of HCl. The ratio of volumes is 1:1:2 small whole numbers. All right, a lot of combining volume. Here we go. You go home and get some balloons and play with them. The whole number ratio 1:1:2 is the same as the mole ratio in the following balanced chemical equation. All right, so Gay-Lussac. All right, so in the volume stoichiometry problem, which is the last thing we'll talk about here, we talk about the mass, volume, and now volume. We will convert a given volume of a gas to an unknown volume of a gaseous reactant or product. There's one step. See? One step. The other one come for 3 steps. One step. So this is cheap. I don't give it to you that much. All right. Convert a given volume to an unknown volume using the mole ratio. Therefore, the volume ratio in the balance equation. So here we go. How many liters of oxygen react with 37.5 liters of sulfur dioxide in the production of sulfur trioxide? So we put a box over sulfur dioxide. Inside that box, how many liters of oxygen react? So 37.5 go in that box. Put another box over the oxygen for X liter. All right. And that delta, what does the delta stand for? The delta over the arrow, a little triangle.
The catalyst?
It's a catalyst, yeah. Well, what kind of catalyst is that?
Heat.
Heat, very good. All right. So therefore, you're making sulfur trioxide. Now, here's the problem. We have the problem up there, all balanced nicely. So we set this up. It's one factor, one factor you need to get there. Isn't that cheap? That's cheap, isn't it? So therefore, I will not give you this kind of problem. About, but we can talk about it. But all right. So manufacturing ammonia, okay? Ammonia, the common household cleaner, is one of the 10 most important industrial chemicals. Almost everybody got this in their home. Household cleaning uses only a small portion of the ammonia produced. Ammonia is very important as a fertilizer in agriculture. So, because the people, you have a one piece of land, and you keep planting things around one piece all the time. Now, in some country where the people have more land, they do what they call shifted farming. They farm here this year, next year they go to another piece of land, farm there, next time they go over here and farm there. But here, you only have one little piece, and so therefore, you're squeezing the neck of that little piece, so you need, and the little land is say, I can't take it anymore. So now what do? You go get fertilizer to rejuvenate, so you can do more planting. That's what ammonia is all about. Very important role. Nitrogen is an essential nutrient for plants. But most plants cannot use atmospheric nitrogen. All right? So therefore, we call bacteria fixing. All right? So we see that, say you are making grilled cheese sandwiches. Many of you probably do. You know how to make that, or you go and buy one. You need one slice of cheese. Now, this concept now we call limiting reactant. Write it down before we start. Limiting reactant. Very, very important to chemical engineers and chemists. Limiting reactant. And a lot of your exam is calling, is blowing whistle on this. You better pay attention to where we are right now. It's called limiting reactant. All right? Say you are making, to give you an example. Say you are making a grilled cheese sandwiches. You need one slice of cheese, 2 slices of bread to make one sandwich. All right? If you have 5 slices of cheese, 8 slices of bread, how many sandwiches can you make? You know the ratio is 1 to 2. 1 cheese, 2 bread. You can only make 4 sandwiches. You will run out of bread before you use all the cheese. So even though you have the cheese there, but you don't have a bread. So therefore the bread is limiting the process of making sandwich. You see that? We call limiting reactant. Very, very important. The guy who ends the show, there's a guy who ends the show. He is a limiting reactant. You cannot do anything, even though you got a whole lot of something sitting out there. Suppose it take 2 donuts to every cup of coffee, 2 donuts. And you got 6 donuts. You got 2 cups of coffee. So you got 2 donuts sitting there. You better not, I dare you. Don't eat that. You don't have coffee for that. So you gotta wait. You gotta go make some more coffee. This process is so important in manufacturing, making anything industrially. Very, very important stuff. Even in your own kitchen, you pay attention when you're cooking, when you're making some food. Certain dishes you want to make. But those things that are limiting, if they're not there, you can't make those dishes. You just cannot. They cannot be those dishes because that ingredient is not there. So this concept is very, very important, and it's on your exam over and over. So pay attention to it. Since you run out of bread first, bread is the ingredient that limits how many sandwiches you can make. So we give you an example of things that you're familiar with. In a chemical reaction, now pay attention now. In a chemical reaction, the limiting reactant is a reactant that controls the amount of product you can make. That's one of the reasons why prices go up. Prices go up. Demand, now in economic, it says supply and demand. You probably heard that before. Supply and demand. When something is in demand and it's not there, prices will go up. Prices will go up. So limiting reactant is a very, very important concept. The limiting reactant is used up before the other reactants. So it will be gone before the other guy just floating around. The other reactants are present, they are in excess. They are in excess. So pay attention to this concept. Very, very important in chemical industry. That's what I do. Okay. I also make cleaning products. But you see, I ran out of some product. I couldn't make the cleaning product. So therefore, I had to wait. I had to put in the order for that item to come before I start making it. I had other things around that I used to make the cleaning product, but I couldn't make the cleaning product because that item was not available. So even if I put the other stuff together, it wouldn't be the cleaning product that I make. So that's very, very important. This is a very important concept in chemistry and chemical engineering. If you heat 2.50 more of Fe and 3.00 more of S, how many moles of FeS are formed? All right? That's one reason why you got to do all your calculation, stoichiometry calculation we talk about, mass, volume. You got to do all that. So you see what will limit the whole process of what you try to make. So 2.5 or more of Fe will react with 2.5 or more of S. 1-to-1. Therefore, iron is the limiting reactant and sulfur is the excess reactant. You got 3.00 more of sulfur. So we take 2.5 of the iron, 2.5 of the sulfur. What's left over is an excess. Sulfur, we cannot make any more FeS. Are you getting the picture? This is a very, very important concept. In all of the reaction we'll be talking about. This is it. This is where the rubber meets the road. So if you start with 3.00 more of sulfur and 2.50 more of sulfur reacts to produce FeS, you have 0.50 more of excess sulfur. So the table below summarizes the amounts of each substance before and after the reaction. Before the reaction, how many moles of iron do you have? 2.50 mole. How many did you have for sulfur? 3.00. How many of the FES you got? You got no FES because you haven't made it yet. So it's 0, 0. Now, after the reaction, what happened? You don't have any more of iron, no more iron, but you got 0.5 mole of the sulfur. Now you've made FES 2.50 of FES. Do you see that there? All right. So now we come to the real problem now. There are 3 steps to a limiting reactant problem. Let me give you time for this one. Take your time. Let's take a little break on this one. Make sure you have them down. Make sure you have them down. We'll spend some time on this one. Slowly, right here. Everything you learn before I pack into this. Pack into this. So everything you learned became prerequisite for what we're about to talk about here. So take your time, write a 3-step down. Make sure you have them down. All right. Number 1, calculate the mass of the product that can be produced from the first reactant. Calculate the mass of the product that can be produced from the first reactant. Mass reactant, 1. Mole reactant. You know, if you have mass, you're going to go to what? Mole, and then you're going to go to mole again, then you're going to go to mass. That's something we learn when we're doing mass, stoichiometry. See that? You see why that stuff is prerequisite? You cannot do limiting reactant if you don't understand all that stuff we talk about. Calculate the mass of product that can be produced from the first reactant. Mass of reactant, 1. Go to mole reactant, 1. Go to mole product. Go to mass of product. Number 2. Calculate the mass of product that can be produced from the second reactant. Mass reactant, 2. Go to mole reactant, 2. There's still mass going. And mole reactant to mass product. Number 3, the limiting reactant is the reactant that produces the least amount of product. You hear that now? So you got A plus B giving you C plus D. So you got to work with A and say, what is the contribution that A can make in making this product? What is the contribution that B can make in making this product? That is an investigation. And that investigation take you back to what? Mass stoichiometry, mass volume stoichiometry, volume stoichiometry. Those are prerequisites. So once you determine that, so when you're making a product, you know what's in excess. What is in excess? We don't even worry about what's in excess. Our focus is on the guy who stops the show. Now take a little break. Take a little break. All right, the break is over. Any questions so far? All right, here's the problem now. All right, here's the real stuff, real stuff. Let's get to the real stuff. How much molten iron? We're gonna make a liquid out of iron. Is formed from the reaction of 25.0 gram of FeO and 25.0 gram of aluminum. So the first thing we need to do is to write the correct equation for this. Balance that equation well. Everything you learn goes into this problem. And we know that it's a how much molten iron, see, molten iron is formed. Where is the molten iron? It's on the product side. So put a box over the molten iron and put what? Is it how much molten iron is formed from this reaction? Put a box there and put an X gram in our box. What's given to us? We're given from the reaction of 25.0 gram FeO, put another box there. In that box, you put 25.0 gram inside our box. Alumina, put a box of aluminum and put 25.0 in there. So we're not going to be bothered with aluminum oxide, so we know what we're dealing with. We are making molten iron. That's our goal. We got two fellows here that can make us make this molten iron, FeO and aluminum. So therefore, what is the contribution for FeO in making molten iron? What is the contribution for aluminum in making molten iron? We're going to find out. So now students say 25.0, the thing is equal. No. Be careful, be careful, be careful. So the first thing is we need to start with the first reactant. Let's convert gram FeO to what? Gram Fe.
Okay, quick question on
Great
that.
question. Who's that?
Chanel.
Chanel, okay.
So how come you choose the molar mass for the iron oxide, I believe, and then you do the atomic weight for just the iron?
Because we are giving molten iron. So in order for you to find out how many mole that is, you need the molar mass. You do the same thing with aluminum, you know, and so forth.
Okay.
What are we making, Chanel? What are we making?
The grams of iron.
Yeah, that's what we're making, right?
Yeah.
What is it? Which contribution will FeO make? And FeO is given in grams. Anytime you see gram, you got to go to mole, right?
Uh-huh.
And when you go to mole, you need what? The molar mass, right?
Right.
Yeah, that's why.
Okay.
So now, first we're going to work with the FeO. Working with FeO simply means we are trying to figure out what contribution FeO will make in making the Fe, which is the molten iron, liquid iron. So we start with a 25.0 gram. Start with that. We need a molar mass for FeO. One more FeO is 71.85 gram FeO. If these numbers are placed down, look at this factor. What is the relationship between the Fe and the FeO from the balance equation? It's 3 to 3. You see that there? 3 moles of Fe, 3 moles of that. That's very important. That's why you need to have the correct balance equation. Now, everything gone within the mass of Fe. So therefore, what is the molar mass for Fe? 55.85. So now, in order to, FeO can make 19.4 grams of Fe. That's FeO contribution. We can produce 19.4 grams of Fe if FeO is limited, right? Okay, so let's see. Now, so we come here, we'll go after the aluminum. Go after the aluminum. What contribution can aluminum make? So we take 25.0 gram aluminum times this molar mass. What is the relationship? It's 2 to 3. So you have that setup right there. And Fe is 55.85, one more. So you see, aluminum can do what? Make 77.6 grams of Fe. All right? Whereas FeO can make what? 19.4 grams of Fe. So which guy will stop the show of making Fe? Who do you think will stop the whole program? Anybody? Who stops the program? Supply and demand. Who stops the program? Can somebody talk? Tell me, between the FEO and alumina, which one is limiting the making of FE?
FEO.
FEO, that's right, because FEO can only produce what? 19.4 grams. Whereas alumina, look, takes a lot of alumina. We know you can do all that, but sorry, we don't have enough Fe to do that. Sorry about that, my friend. We know you're willing to make 77.6 grams. But there's no FeO around, my friend. I'm sorry. You are in excess. You are in excess. Do you see what we're talking about here? So before manufacturing can take place, you see what people have to sit down and do all these calculations before they start making stuff? Yeah. So when you go to the store to buy something, you complain, oh, this is so expensive. Oh, no. Boy, you don't know what people go through making these things. Any questions so far before we move forward?
I have a question, Professor.
Yeah, please.
So
who's asking?
Adriana.
Adriana, all right.
My question is just I'm looking at the equation, and for the third part where it's 3 mole iron over 2 mole aluminum, you got the 3 and the 2 from the coefficient.
From the coefficient, yeah.
Okay, and then just one more question.
Mm-hmm.
So iron is the one that's limiting because it's
no, not iron. What's limiting? It's iron we're trying to make. So iron cannot limit. What's limiting?
Aluminum.
Oh, aluminum.
No.
FeO.
FEO.
FeO. Look at the reactant. Don't confuse yourself. Look at it. We are working with a reactant. All right? The contribution that the reactant make in making something that happen. Do you see that now?
Can you repeat that?
Okay. The contribution, suppose even it's every day, even at home. Somebody the person who has more money and the other person who has less money, and they're trying to do something together, and they want to have less money run out, can't do it anymore, so they can't do it. All right? So you see here, the FeO and alumina is in the business of making Fe. You see that now? The goal is to make Fe. But look at the starting material. They both got the same starting material. In this case, it's not always the case. FeO is 25.0 grams. Alumina is also 25.0 grams. 25.0 grams of FeO and 25.0 grams of alumina. You're gonna react them. When you react them, we're gonna make Fe. So actually, this reaction is only making 19.4 grams. And it stops there. All right? But aluminum is in excess, can produce 77.6 grams of Fe if alumina is limiting. Is that clear so far? The last one? This one? Okay. So the limiting reactant is a very beautiful concept, but all the prerequisites we passed by before we got to it. Mass, mass, volume, volume in consideration in chemical reactions. So the chemical engineers do things on a large scale because they are going for the dollar sign, for the market. The chemists do things on a small scale. They work together. In a typical industry, you have a lab there, and the chemists are in there working, doing things on a little scale, small scale, and the chemical engineers are the one that design the factory, and they're gonna make things for the market, but they cannot sell. So now we need people that got a business sense to kind of help sell what is made. They come to MBAs and all the other people. They can't make an MBA, they can't make anything, but they know how to, to sell stuff. Everybody work together like that. All right. So any questions on limited reactant? We've still got more to go. All right. So let's compare the two reactants. It's time to compare them. 25.0 gram of FeO can produce what? 19.4 gram of Fe. 25.0 gram aluminum can produce 77.6 grams. FeO is the limiting reactant. Aluminum is the excess reactant. Is that clear so far? Everybody? Any questions so far? So limiting reactant on the exam, you'll be able to know how to deal with it. So you need to ask some questions. All right. So let's come to volumes of gas. Limiting reactant problems involving volume. Involving volumes follow the same procedure as those involving masses, except we use volume in this case. Volume of reactant, volume product. We can convert between the volume of the reactant and the product using the balance equation, same concept. Just remember now, stoichiometry takes in three forms: mass to mass, mass to volume, volume to volume. So how many liters of NO2 gas can be produced? I mean, it can be produced, meaning it's going to be on the product side from 5.00 liter of NO gas and 5.00 liter of O2 gas. So you set the reaction up. NO, and this is a homogeneous system because all this is the same. So NO2 is colliding with O2 with the help of a UV light as a catalyst to make NO2 brown color gas, NO2. I've seen it, that's why I know. All right, convert LNO to LNO2. So in other words, we would say what contribution NO will make in making NO2. We deal with that. Then we say what contribution O2 makes in making NO2. Those are the thick questions. So you got 5.00 of that factor. So you're talking about from volume to volume. So, that's a cheap problem. All right, so therefore you got that. So NO will make what? 5.00 liter of NO2, and O2 will make about 10.0 liter, double the amount. All right, so which one is limiting? Which is in excess? So here we go. Let's compare the two reactants. 5.00 liter NO can produce 5.00 liter of NO2. 5.00 liter O2 can produce 10.0. So therefore, NO is the limiting reactant. This is the volume here. All right, O2 is in excess. Same, the concept is the same.
So if the number that you get, so if you have 5.00 of the nitric oxide and then 10.00 Wait, is that yeah, the same thing. So the smaller one is the
Limiting reactant.
okay.
Yeah, you got that now?
Yes.
The other one is other one is in excess.
Okay. Thank you.
Okay, when you perform a laboratory experiment, the amount of product collected is the actual yield. What you collect from the laboratory experiment, we call that the actual yield. What it's supposed to be is a theoretical, in theory, what it's supposed to be, but you didn't get it. So limiting reactant play a very important role. Again, the amount of product collected from a limiting reactant problem is a theoretical yield. So when you have a limiting reaction problem, the smaller one, which is less than the other one, the excess. So when you're doing a theoretical problem, when you're doing a yield, a theoretical problem, that one is considered to be the theoretical yield. So the percent yield then is the amount of actual yield compared to the theoretical yield. So actual yield over theoretical yield times 100% is percent yield. So people, the organic chemists, you know, they will squeeze the neck of a reactant because they want a bigger yield. So they will squeeze. All right. So here we go. Suppose a student performs a reaction like you and obtains 0.875 grams of copper carbonate. And the theoretical yield is 0.989. The theoretical yield is telling you that if you are doing a limiting reactant, that number will be 0.998 grams. That's right. What is the percent yield? You write the equation down. Get the equation here. You balance the equation. Then you find out you got the two reactant, copper nitrate, you got sodium carbonate. Check to see what each of them will produce. Again, what is it? What is the limiting reactant? Do you see it? You see what we're talking about here? Okay, once you get a limiting reactant, that limiting reactant becomes your theoretical yield. And what you collect in a lab, from the lab you do, that is the actual. So usually, students will waste things back, you know, in the process of making something, they lose a lot of stuff. So you want to be very careful in the lab so you can't be losing a whole lot. So that student, if everything went well, you're supposed to have what? 0.988 grams of copper carbonate. But everything didn't go well, they lost a lot. So they got 0.875 grams of. So now, what is the yield? They got 88.6%. Not so bad, but you probably want to put something close to 100%. So this is how so the reason why the limiting reactant is important, it's very, very important in finding out what yield do you have, is because you're trying to figure out which one is the theoretical yield. And that theoretical yield is the one that has a limiting factor on it. Limiting factor. So that's why it's so important. Any questions so far? Of theoretical yield and actual yield. Percent yield. You might have this in your exam. So if you have this in your exam, know that number one, you're going to do what? Write an equation, balance the equation, figure out the limit, what's limiting before you come to this level. Now, this is the kind of problem I like to get. It's a good chunk of work. See, I'll make you work. I will make you work. By the time you gotta leave this class, you'll be okay. You'll know stuff. See, no break. Anybody that take Dr. Tukwu's classes, there's from the day you start, you keep working, you keep working you, making a workhorse until the last day when you drop that pencil. and so the final exam, yay! You're gone. But on the day you enter my class, you better start working from that day to the end. All right. That's why students like to come to my classes, because they want to work. They love to work. And I see why you came. Because I knew you're a hardworking student. All right. The coefficients in a balanced chemical reaction are the mole ratio of the reactants and products. The coefficients in a balanced chemical reaction are the volume ratio of gaseous reactants and products. We can convert moles or liters of a given substance to moles or liters of an unknown substance in a chemical reaction using balanced equation. So important. All right, limiting reactant. What is it? It's a reactant that is used up first in a chemical reaction. Used up first. Once it's done, nothing else goes on because it's not there to keep it going. The theoretical yield of a reaction is the amount calculated based on a limiting reactant. So to get a theoretical yield, you got to do the limiting reactant concept. You got to do that to determine the theoretical yield. Otherwise, you cannot determine the theoretical yield. The actual yield is the amount of product isolated in actual experiment. Things that you collected, you dry some stuff, you heated some stuff, you put it together. So the percent yield is the ratio of the actual yield to the theoretical yield.
Okay, so the theoretical yield is just something you assume is gonna.
You're not going to assume that. You're going to do you're going to calculate that from using limiting reactant.
Okay.
Yeah. So whatever is limiting reactant becomes a theoretical yield.
Okay.
Okay? All right. Now, so that's it. Any questions so far? Any previous slides you want to go back to? I can go back to that. You got any question? Everybody okay? Well, if you don't have any questions, you're okay. Let's call it a day. Okay?
Okay.
So tomorrow, which is Tuesday, we will do chapter 10, gases. Make sure you prepare for that. And those of you that have lab this afternoon, you got Boyle's law, pressure, and volume. We'll see more of Boyle's law on Tuesday. We'll discuss that, all the different laws, Charles's law, Boyle's law, Gay-Lussac, Avogadro, all those will be talking about on next week, Tuesday. So have a very blessed day, and I'll see you for those of you this afternoon, I'll see you this afternoon. And those that will not see this afternoon, I'll see you next week, Tuesday.
Thank you.
Okay?
Likewise. Thank you.
That's right. You take care now. Take care. God bless. I hope you learned something today.
Thank you.
Yes, we learned a lot.
Thank you. Bye-bye.
All right.